Time could be reversed at a molecular level in materials like glass, according to new evidence discovered by physicists. The study suggests that time may be able to flow both forward and backward, particularly in microscopic systems. Although the laws of physics often ignore the direction of time, the second law of thermodynamics dictates that systems inevitably become more disordered over time, creating a so-called arrow of time. However, glass, an amorphous solid, ages in a unique way that doesn't rely on external forces but on its own internal entropy-driven changes. This aging process, described by physicists as material time, had never been experimentally measured until now. Using a highly sensitive video camera and laser light, the researchers tracked molecular movements within glass-forming substances, revealing that, on a small scale, particles within the glass appear to push and pull each other in reversible ways. Despite this finding, the overall aging of the material remains irreversible due to entropy. This phenomenon shows that on a quantum level, time may not behave as it does in larger, macroscopic systems. While quantum superpositions allow systems to move in both time directions, humans, being macroscopic, cannot perceive these changes. The study deepens the understanding of time, but these microscopic behaviors don't translate to a human experience of time. Though these quantum insights add complexity to our understanding of the universe, we remain bound by the forward progression of time in everyday life. Time seems to move faster as we age because our brains and lives become more routine, unlike during adolescence, when rapid changes create a sense of novelty and slow down our perception of time. In adolescence, the brain is highly adaptable and elastic, soaking up new experiences and hardwiring them into our development. This creates the feeling that time moves slowly, as every day brings something new. As adults, our lives tend to settle into consistent patterns, with fewer new experiences, making time feel like it flies by. To combat this sensation, experts suggest mixing up routines, focusing on the present moment, and appreciating the stability adulthood provides. From an experiential standpoint, the busyness of adulthood, packed with responsibilities and commitments, can leave little room for savoring moments and reflecting on the passage of time. On the other hand, childhood often allows for more unstructured time and greater attention to the present. The accumulation of memories and experiences also impacts our perception of time. As we grow older, we have a vast library of past events to reference, making recent events seem relatively insignificant and time feel compressed. While adolescence is filled with memorable experiences, studies show that life satisfaction increases steadily as we age, reaching a peak around 70 years old. By embracing the present and savoring the consistency of adulthood, we can shift our mindset to see the passage of time as something positive rather than a source of anxiety.
Have you ever wondered how scientists calculate the age of stars, including our sun, which is estimated to be approximately 4.57 billion years old? Despite being unable to sample stars physically, astronomers have developed sophisticated techniques to unravel their age and lifespan. There are a few different obstacles to estimating the age of a star, but the general estimation is much easier when a star is in a cluster. The majority of stars spend around 90% of their lifespan in the main sequence phase, during which they emit a constant stream of energy and radiation from their internal nuclear furnace. In the main sequence phase, the characteristics of a star, such as its brightness and temperature, remain relatively constant. The most massive stars are blue-hot in color and have intense brightness, while the least massive stars appear red-hot and relatively faint. The relationship between a star's mass, brightness, and age allows astronomers to derive crucial information from star clusters. The mass of the star tells us how much fuel it has, while the brightness tells us how fast it is burning that fuel. Therefore, it is possible to roughly calculate the age of the star and, subsequently, the age of the other stars in the cluster. Technological advancements, such as the Kepler Space Telescope, have significantly contributed to understanding lone stars. The telescope enables direct observation of stars and the detection of star spots, dark patches on their surfaces. These star spots offer valuable insights into a star's spin rate, directly linked to its mass and age. Another technique called gyrochronology relies on a star's rotational speed. As stars rotate, their speed gradually changes depending on their age and color. By determining a star's color and rotational speed, scientists can estimate its age with an uncertainty of 15%. For example, our sun is projected to last another 7 billion years before transforming into a red giant star. By employing these innovative methods, astronomers have made remarkable progress in understanding star ages and their evolution. Accurate estimation of star ages enhances our comprehension of stellar life cycles obstacles and aids in the search for intelligent life beyond our planet.